Okay, here we are going to do some examples on how to find the limiting reactants. Okay, there are three ways to find the limiting reactants. Method number one, separately calculate the amount of product that would come from each reactant. I repeat, separately calculate the amount of product that could come from each reactant. The reactant that produces the smaller amount of product is limiting. Let's do that. We are going to use this example. Given the indicated number of moles, identify the limiting reactant of the following reaction. Step number one, what is a limiting reactant? A limiting reactant is that which is going to be completely consumed in the reaction, no leftover. Completely consumed or completely used up, no leftover. So, and you want to also find the limiting reactant from the left side of the reaction because it's called a limiting reactant. You will not find it on the product side. It has to be on the reactant side of the reaction. So let's use method number one here. We are saying that we can separately calculate the amount of product that could form from each reactant. The reactant that produces the smaller amount of product is the limiting reactant. So let's firstly test the first reactant, which is methanol. How much product? We are using method 1 to find the limiting reactant. So how much product? Allow me to just write it as PDCT possible. Okay, so how much product possible from methanol? Now you ask, which product are we looking at? Let's just test CO2. You can choose even water, but let's test CO2. How much product is possible if methanol is limiting? So this is how we are going to do. We are going to rewrite our chemical equation. 2 methanols react with 3 oxygens to give us 2 CO2s and 4 H2Os. Our reacting ratio is gonna go with the leading coefficients. My focus is just gonna be the relationship between the methanol, this is methanol, and the carbon dioxide. So it's the reacting ratio is 2 to 2. Alright, I'm trying to test to see if methanol will be completely consumed, but I have to find, using method 1, how much of product CO2 will be formed, and then the next time I'll test how much product will be formed if oxygen was limiting. Whoever is going to give me, whichever reactant, methanol or oxygen, that will give me the least amount of CO2 will be the limiting. So let's go. So I'm given in the problem that the reaction is happening with 1.5 moles of methanol, but I really want to find the yield of CO2. I can go to moles. So I'm going to go to moles of CO2. For every 2 moles of CO2, I must have reacted 2 moles of methanol. You are asking, where did I get those 2's? From the balanced equation using the coefficients, the numbers 2 and 2. Now, if I do the math here, this tells me that the amount of CO2 possible if CH3OH was completely consumed would be 1.500 moles of CO2 possible. Okay. Now next, I'm going to test, that was for methanol. Next, I'm going to test how much is possible if oxygen was limiting. So in this case, I'm going to compare the moles of oxygen 3 to the moles of CO2 2. So I'll take my given moles in the reaction 0.5. So I'm given 0.500 moles of oxygen, but I want to see how much CO2 will be formed. So for every 2 moles of CO2 in the factual balanced equation, I must have reacted 3 moles of oxygen. Now if I do the calculations here, how much CO2 will I get? Remember, the moles of oxygen will cancel, just like here, moles of methanol cancels, which is why we want to set these conversion factors in this way and not the inverse of them. You have to have the conversion factors set up correctly. Now let's do the math and see what we get. So we have 0.5 and I'm multiplying it by 2 and then I'm dividing by 3. So the answer is 0.333 moles recurring of CO2 possible. Now remember, with method 1, we are saying that the reactant that produces the smaller amount of product will be the limiting. Who is producing the smaller amount of product here? It's gonna be the oxygen. So oxygen is producing, according to method 1, oxygen is producing the least amount of product, which is CO2. That means that oxygen is indeed the limiting reactant. Oxygen is the limiting reactant. So that is method 1 of finding the limiting reactant. Let's do method 2. So in method 2 of finding the limiting reactant, divide the moles of each reactant by its coefficient. The reactant with the smallest quotient is a limiting reactant. I repeat, divide the moles of each reactant by its coefficient. The reactant with the smallest quotient is the limiting reactant. What is a quotient? Quotient is just the ratio. Okay. Now let's try this. So same problem. Given the indicated number of moles, identify the limiting reactant in the following reaction. Okay, so we have methanol provided 1.500 moles, oxygen provided 0.500 moles to give you 2 moles of CO2 and 4 moles of water. That's what you are given as a question. So we need to identify the limiting reactant. That's what we need to do. So using method 2, divide the moles of each reactant by its coefficient. So let's do that and see. The reactant with the smallest quotient is the limiting reagent. So now this is what we're going to do. I'm going to take my methanol and test to see if it's limiting. What is the coefficient of methanol? 2. What is the amount given? 1.5. So I'll divide the amount of methanol by its coefficient 2. I'm getting the quotient to be 0.7500. The quotient is just the ratio, okay, the fraction. So that is the quotient of methanol. And then now I test oxygen. Oxygen amount is 0.500 moles. Divide by its coefficient number 3. The answer should be 0.167. Which of these two gives you the least quotient? The method 2 tells us that the reactant with the smallest quotient is the limiting reactant. So again, it's going to be oxygen. So we'll say here, oxygen has the least quotient according to method 2. Therefore, oxygen reactant is the limiting. It's going to be completely consumed in this reaction and methanol will have leftovers. That's the idea. Now we are on method 3 of finding the limiting reactant. Method 3 reads, find the amount of each reactant needed to completely use up the other reactant. Disregard the scenario that requires more of a reactant than is actually present. This method is actually what we have on our slide. in our PowerPoints or in our PDF or in our notes. It's this method 3, where you find the amount of each reactant needed to completely use up the other. So now let us test how much methanol is needed to completely consume the oxygen. So in that case, if I'm testing for methanol to see how much it's needed to completely consume the oxygen, which is what you're asked to do, find the amount of each reactant needed to complete use up the other. So I'm going to take my oxygen and assume that my oxygen is completely used up. Multiply by their ratio. Okay, so what I'm given here is for every 2 moles of methanol, that is the mole ratio or conversion factor, if you want to call it mole to mole ratio, that's what we're going to use here. For every 2 mole of methanol, we seemingly need 3 moles of oxygen. So how much methanol is needed to completely use up the oxygen? So once you set it up like that, it gives you the opportunity to cancel out moles of oxygen. The answer will be moles of methanol, and that will tell us how much methanol is required to consume all the oxygen. So we do the math again, it will be 0.5. We're going to multiply that by 2, and then we divide by 3. It's giving me 0.333 recurring moles of methanol needed to completely consume all oxygen reagent. So that is test 1. Test 2, we are going to test how much oxygen is needed to completely consume 1.5 moles of methanol. So we know that we are given 1.5 moles of methanol, and we are trying to see how much oxygen is needed to completely consume all this methanol, assuming all this methanol 1.5 moles is limiting. So I'm going to multiply by the mole to mole ratio. This time the oxygen will be the numerator, the methanol is gonna be the denominator. I'm taking just the reacting quotient, 2 methanols, 3 oxygens from the balanced equation of reaction. Now if you do this calculation, it will be 1.5. Let me pull this up. It will be 1.5. I'm going to multiply by 3. I divide by 2. It's giving me 2.25. Yeah, 2.25 moles of oxygen is gonna be needed to completely consume all methanol. Now, so which one do you think, which of these two do you think is limiting? You can tell that what you have available for oxygen is only 0.5. The amount of oxygen available is 0.500 moles. That is way less than what is needed to completely consume all methanol. So that tells you that oxygen is the limiting reagent. So oxygen is the limiting agent. That is the idea. Now you might be wondering, so which method do you prefer to use in finding the limiting reactant? Honestly, I would prefer method 1 because it not only tells me the limiting reactant or reagent, but also gives me what we call the theoretical yield, the amount possible of the product formed, the possible amount of product that can be formed. So that is the advantage of method 1. You see how method 1 says separately calculate the amount of product that could be formed from each reactant. That amount of product that could be formed from the limiting reactant is what we call the theoretical yield. So for example, I can still walk you back on this. When we tested methanol to see if methanol was limiting, we multiplied the amount of methanol by the mole ratio of one of the products, CO2, to the methanol, which is 2 to 2. The amount of possible CO2 formed would be 1.5 mole. This is what we would call the theoretical yield of CO2, meaning if everything goes well, this is the maximum amount of CO2 that can be formed if methanol was limiting. Now, if oxygen was limiting, we did the same thing. We took the 0.5 moles from the equation and multiplied by the ratio of the oxygen to the product CO2, or the product CO2 to the oxygen. The reaction was for every 3 moles of oxygens, using the coefficient, you get an equivalent of 2 moles of CO2. That's how we got this conversion factor. Now, if you multiply 0.5 by the conversion factor, you get 0.33. Now you see, compare 0.333 and 1.5. Who is the limiting reagent? It will be oxygen. And that oxygen dictates the actual theoretical yield. So it will not be the methanol, because methanol is giving us a lot. We want the one that limits the amount of product that we are getting. So we say that oxygen is a limiting reactant, and the true theoretical yield of the product CO2 will be 0.333. So the theoretical yield, true theoretical yield of product CO2 is 0.333 mole. So you see, which is why I prefer using method 1, because it's going to tell me the limiting reagent, the oxygen, and it's going to tell me the true theoretical yield of the product. I can find the theoretical yield of CO2 using oxygen now, and then I can find the theoretical yield of water using the same oxygen. Oxygen is a limiting reactant, which is why I prefer method 1.